Recording in progress. So everything has a pattern, everything has a sequence, and this sequence will enable us to move to the next level. Okay, that's what we are going to do. Numbers and sequence. I know numbers are beautiful. If they aren't beautiful, nothing is. Paul Erdos. Actually, a lot of people have this problem. They think mathematics is the toughest subject because they are not understanding the beauty of it. When they understand the mathematics properly, they will love it. They will go beyond anything. This person, our great Srinivasa Ramanuja, was an Indian mathematical genius who was born in Erode in a poor family. He was a child prodigy and made calculation at lightning speed. He produced thousands of precious formulas, jotting them on his 3 notebooks, which are now preserved at the University of Madras. With the help of several notable men, he became the first research scholar in the mathematics department of University of Madras. Subsequently, he went to England and collaborated with G.H. Hardy for 5 years, from 1914 to 1919. He possessed great interest in observing the pattern of numbers and produced several new results in analytic number theory. This mathematical ability was compared to Euler and Jacobi. They are one of the most famous. They are one of the most famous people who work. All right, most famous people. Euler and Jacobi, the two great mathematicians of the past era. Ramanuja wrote 30 important research papers and wrote 7 research papers in collaboration with G.H. Hardy. He has produced 3,972 formulas and theorems in very short span of 32 years. 32 years lifespan. He was awarded BA degree for research in 1916 by Cambridge University, which is equivalent to modern day PhD degree. For his contribution in number theory, he was made Fellow of Royal Society, FRS, in 1918. His works continue to delight mathematicians worldwide even today. Many surprising connections are made in the last few years of work made by Ramanuja nearly a century ago. What and all we are going to do now? 1 minute. What and all we are going to study at the end of this chapter, you would be knowing what is Euclid division lemma, to understand Euclid division algorithm, to find LCM and HCF using Euclid division algorithm, to understand the fundamental theorem of arithmetic, to understand the congruence modulo n, addition modulo n, and multiplication modulo n, to define the sequence and to understand sequence as a function, to define an arithmetic progression and geometric progression, GP, to find the nth term of AP and its sum to n terms, to find nth term of GP and its sum to n terms, to determine the sum of some finite series such as sum of n terms, sum of n squared terms, sum of n cubed terms. All these we are going to do. First, to understand Euclid's, we have to understand a lot of things. Okay. Introduction. The study of numbers has fascinated humans in several thousands of years. The discovery of Libombo and Ishango bones, which existed around 25,000 years ago, has confirmed the fact that humans have made counting process for meeting various day-to-day needs. By making notches in the bones, they carried out counting efficiently. Most considered that these bones were used as lunar calendar for knowing the phase of moon, thereby understanding the season. Thus, The bones were considered to be the ancient tool for counting. We have come a long way since the primitive counting method existed. It is very true that the pattern exhibited by numbers have fascinated almost all professional mathematicians, right from the time of Pythagoras to current time. We will be discussing significant concepts provided by Euclid and continue our journey of studying modular arithmetic and knowing about the sequence and finite series. These ideas are most fundamental to your progress in mathematics for upcoming classes. It is time for us to begin our journey to understand the most fascinating part of mathematics, namely the study of numbers. Okay, good. Almost 25,000 years ago, the boneல குட்டி குட்டி மார்க்கிங்ஸ் பண்ணியிருக்காங்க. ஒரு குரூப் பண்ணியிருக்காங்க. இப்ப இந்த பிக்சர் பார்த்தாலே நம்மளுக்கு வந்து தெரியும். குரூப்பிங் பண்ணியிருக்காங்க. குரூப்பிங் பண்ணிட்டு ஓகே இவ்வளவு நாள் அப்போ கிட்டத்தட்ட ஆல்மோஸ்ட் இட் இஸ் கன்சிடர்ட் நம்மளோட மூன் சார்ட். பௌர்ணமி வர்றது, அமாவாசை வர்றது, ஆல்ரைட், ஃபுல் மூன் டே அண்ட் நோ மூன் டே, இதை பேஸ் பண்ணி ஹவு மெனி டேஸ் கம்ப்ளீட்டட், அவங்க சம் பேட்டர்ன்ஸ் அவங்க ட்ரை பண்ணியிருக்காங்க. ஸோ they started counting in different methods by crossing the bones. அதுல கீறது மூலமா போன் இருக்கு, ஒரு போன் இருக்கு, அந்த போன் பீஸ்ல மார்க்கிங். ஓகே, இப்போ நம்மளோட மார்க்கிங் போடுறோம்னா 1 2 3 4th day we are working, alright, 4th day. So like that, okay, இதெல்லாம் வந்து ஒர்க் பண்ணிருக்கோம், இவ்வளவு டைம் ஒர்க் பண்ணிருக்கோம் நம்மளால கொடுக்க முடியும். அதேதான் அதுக்காக தான் யூஸ் பண்ணிருக்காங்க. ஃபார் லூனார் கேலண்டருக்காக இதை யூஸ் பண்ணிருக்கோம் இந்த போனை அப்படின்றது அந்த அவங்களோட பெர்செப்ஷன். பட் வாட் எவர் இட் இஸ், தே ஹேவ் ஸ்டார்டட் கவுண்டிங். தே அண்டர்ஸ்டுட் தி number system 28,000 years ago to maintain the day to day activities. இதுதான் நம்ம இதுல பாக்குறோம். அப்போ கொஞ்சம் கொஞ்சமா பித்தாகரஸ் வந்து ஒரு ஃபார்முலா சொல்லுவாங்க. பித்தாகரஸ் அப்படின்னு கிட்டத்தட்ட அந்த hypotenuse square equal to sum of square of other two sides. ஆனா that is one of the smallest part. பித்தாகரஸ் வந்து இன்னும் நிறைய பண்ணிருக்காரு. அவரோட அந்த புக்கை பார்த்தாலே இவ்வளவு பெருசு இருக்கும். சி மிஸ்டர் ராமானுஜமே 3962 ஃபார்முலாஸ், எத்தனை தியரிஸ், எவ்வளவு அதை ஃபார்ம் பண்ணணும். அந்த ஃபார்முலாஸ்லாம் ஃபார்ம் பண்ணணும்னா சும்மா ஃபார்ம் பண்ண முடியுமா? அதுக்கான எஃபர்ட்ஸ், அதுக்கான புக்ஸ், அதுக்கான பேப்பர்ஸ் பிரசன்டட், எல்லாமே எதுக்காக இவ்வளோ பண்ணாங்க? தேர் இஸ் சம் ரிக்வயர்மெண்ட். அப்ப அந்த மேத்தமேட்டிக்ஸ் நம்பர் சிஸ்டம் அண்டர்ஸ்டாண்ட் பண்ணிட்டோம்னா ரொம்ப அழகா நம்மளால எந்த ஒரு விஷயத்தையும் அணுக முடியும். அதுக்காக தான் நம்ம வந்து ஒர்க் பண்ணிட்டு இருக்கோம். யூக்ளிட் டிவிஷன் லெம்மா. Euclid, one of the most important mathematicians, wrote an important book named Elements in 13 volumes. 13 book. The first 6 volumes were devoted to geometry, and for this reason Euclid is known as father of geometry. But in next few volumes he made fundamental contribution to understand the properties of numbers. One among them is Euclid division lemma. This is simplified version of a long division process that we are performing for division of numbers in earlier classes. Let us now discuss Euclid's lemma and its application through an algorithm termed as Euclid division algorithm. Lemma is an auxiliary result used for proving an important theorem. It is usually considered as a mini theorem. ஒரு பெரிய ஃபேக்டை நம்ம அண்டர்ஸ்டாண்ட் பண்றதுக்கு குட்டி குட்டி தியரம்ஸ் தான், குட்டி குட்டி விஷயமா வந்து ப்ரூவ் பண்ணிட்டு அது மூலயமா ஒரு பெரிய கான்செப்ட பண்ணணும். அதுதான் லெமா அப்படின்னு சொல்லி ஒரு ஸ்ட்ராங்கான ஒரு அல்காரிதம் வித் நம்பர் சிஸ்டம் பண்றோம்னா, இன் கம்ப்யூட்டர்ஸ் நம்ம அல்காரிதம் தான் சொல்றோம், ப்ரோக்ராமிங் பண்றோம், எல்லாமே அல்காரிதம் தான் சொல்றோம். அப்போ இந்த இடத்துல லெமா மீன்ஸ் ஸ்மால் ரிசல்ட் proving towards a big theorem. That is Euclid's division algorithm. Lemma, it is also known as lemma. First theorem. Euclid's division lemma let a and b be any positive integers, then there exists a unique integer q and r such that a equal to b q plus r, where r is lesser than greater than or equal to 0, definitely lesser than b. The remainder is always less than the divisor. Number 1, r equal to 0, then a equal to bq. So b divides a completely. Conversely, b divides a, then a equal to bq. If b divides a equal to bq. So what they are trying to specify here, think about this. Give a number, two digit number, 32. Another number, single digit number, 9. Okay, 32, 9. If I divide 32 by 9, what I would be getting? 3 times 27, remainder 5. So this 32, this is A, this is A, this is B, this is quotient, this is remainder. All right. So this 32 can be written as BQ, BQ, okay, BQ plus R. That is 3 into 9 plus 5, 27 plus 5, 32. All right. So this remainder, if it's 36 here, then 36 equal to 4 into 9. Q is 4, 9. So there is no remainder. Remainder is 0. Remainder can be greater or equal to 0 for this 9 as a divisor. 0, 1, 2, 3, 4, 5, 6, 7, and 8. These are the remainders we can get. We can't get the remainder greater than or equal to 9. All right. It should be from 0 to 8. That's the concept they are trying to prove here. That's the concept they are trying to prove here. So A equal to BQ plus R. If I substitute it here, A divided by B, A divided by B gives a quotient Q and a remainder R. All right. So A equal to BQ plus R. That's what Euclid division lemma tells about. All right. So we are going to apply this concept and see where and all it leads to. If R equal to 0, what happens? This will get cancelled. So A equal to BQ. Conversely, in opposite side, if B divides A, B divides A, definitely it will be A equal to BQ. It is also a converse of it. Right? So, example, we have 32 cakes. Each can hold 5 cakes only. How many boxes we need to pack and how many cakes are unpacked? 34 cakes, 5 cakes only. 5 cakes, each box 5 cakes only. How many boxes we need? We need 6 plus 4. All right, 4 will be left out. So this is A is 34, B is 5, quotient is 6, 4. So 30 plus 4, 34. 5 into 6, 30 plus 4, 34. Okay, that's how we will be getting the result. So the above lemma is nothing but a restatement of the for long division process. The integers q and r are called quotient and remainder. Q and r are called quotient and remainder respectively. When a positive integer is divided by 2, the remainder is 0 or 1. So any positive integer will be forming 2k plus 1, and for some integer k. Integers, it can be They are given it as positive integers. What is a positive integer? Also known as positive integers, also known as numbers. Yeah, natural numbers. Positive numbers, integers are also known as natural number. It will be denoted as z as integer, negative to positive. If they denote it as z plus, then it means positive integers. So that will be natural number also. Zero will not be included there. All right, natural number also. Generalized form of Euclid division lemma. If a and b are any two integers, there exists unique integer q and r such that a equal to bq plus r. This is what we found out. Find the quotient and remainder when a is divided by b in the following cases: a equal to minus 12, b equal to 5. A equal to minus 12, b equal to 5. All right. Then a equal to 17 and b equal to minus 3. A equal to minus 19, b equal to minus 4. Do you have your note with you? Try working this out. I want this. I want you to understand this properly. All right. What would be the quotient, remainder, and the Euclid's form? That is, I want you to divide and exactly specify in this form: a equal to bq plus r. All right. A equal to bq plus r. That's the question. Yeah. Third question. minus 12, this is minus 10, minus 2 into 5, minus 10. So it would be different, isn't it? So the division algorithm, when it's concerned with positive and negative integers, it's not the same like what we do with the regular basics. The division algorithm itself will be changing. So the normal division algorithm will be fine for positive alone, natural numbers alone. For integers, which is a and b is concerned with negative and positive, positive and negative, or negative negative, it will be totally different. That's where we are missing here. So let's check the possibility. Generally, this reminders should be positive reminders alone. There should not be any negative reminders. It should be a equal to bq plus r. There should not be any negative reminders. The reminder should be a positive term. So check here. Minus 12, minus 12 and 5. Minus 12 and 5. So according to Euclid division lemma, a equal to bq plus r, where r is an positive modulo. Positive. R can be positive alone. 0 to positive. That's what we saw. It can't be negative at all. All right. You got minus 2 there. How is that possible? All right. The division itself, we have to be careful, isn't it? So, how this minus 12 can be written? To convert this, we need a set of pattern. Maybe if we add 3 to it, plus or minus 3. Check here. Minus 12. Sorry. Check here. Minus 12 minus 3 plus 3. This would become minus 15. This can be divided by 5 into 5 into minus 3. B Q. All right. B is 5. Q is 3. Plus 3. R is the remainder. All right. See the difference? What we can do? We have to convert things according to the requirement. All right. Check about this. If you are strong enough, you would be getting the result immediately. Minus 12. Okay. Minus 15 plus 3. Minus 12. So is there any other way of representing this? We can see. Is there any other way of representing this also? And accordingly, we can get the result. All right. Then here at 17 plus 17, B is minus 3. All right. So plus 17 and minus 3. We need BQ. We know this is B is minus 3. We have to know Q plus remainder. So 17 can be written as minus 3 into minus becomes plus 15 plus 2. This is minus 5 into minus 3. 15 plus 2. So Q is minus 5. R is remainder plus 2. Positive. All right. Lesser than, greater than or equal to 0. Lesser than B. All right. Modulus of B. Lesser than modulus of B. That is positive B. All right. Modulus of B. That is the choice which we have. Check about this. Minus 19. Minus 4. So I need a number such a way that it should be completely divided by 4. It can be minus 3 or plus 1. 19 minus 3 or plus 1. If I go for minus 3, it will be difficult for me. So I have to convert it into different form. How I can convert? Minus 19 minus 1 plus 1. So this becomes minus 20. So this minus 20 is, we already know b is minus 4. Minus 4 into 5 will be giving minus 20 plus 1. So the quotient is 5, remainder is 1. Alright. We have to think properly regarding the desired result. What I need. What I need. It can't be in negative terms. That's where you went wrong. Alright. That's where you went wrong. Understanding the pattern will enhance you, or else your system of working will be good with positive numbers alone, positive integers alone. Negative integers, when we concern with positive, negative integer, negative, negative integer, negative and positive integers, it will be totally different. We have to form this format: a equal to bq plus r. A equal to bq plus r. Lot of people wouldn't understand this theory, and they will just copy this and proceed on. That is not a possibility for us. See, in this progress check, first and second, it will be okay for you. But from here, it will be totally different. All right. It will be totally different. Minus 4. So, how I can segregate this? (21), 20 plus 1. All right. So, one is minus 4, then another should be minus 5. Minus 4 into minus 5 plus 1. B is minus 4. We have to find Q. All right. Minus 4 into minus 5, we'll be getting the answer 20 plus 1. What about this? Minus 32 minus 12. B is 12. 12. Good. Minus 32 minus 4 plus 4. This becomes minus 36. So, easily we can say that it is minus 12 into 3, which is minus 36, plus 4 would be giving the result minus 32. Here it is negative, this one is positive. So, when we will get minus 31 minus 4 plus 4. So, this is minus 35 plus 4. Now, we can segregate this as 7 into minus 5 plus 4. So, this is B, this is Q, this is R. All right. So, that's how we have to convert this Euclid division lemma. All right. Okay. Let's consider the following example. Show that square of an odd integer, okay, may I note it, it's an odd integer, is of the form 4q plus 1 for some integers q. We are just going to apply the theory and check whether it is how to proceed with it. These kind of sums, odd integers, they can ask for even integers also. All right. Odd integers is 4q plus 1 we have to prove. Let x be an odd integer. Okay, x be an odd integer. Since any odd integers is one more than the even integers, we can say that it is 2k plus 1. If I substitute k equal to 0, x equal to 1. If I substitute k equal to 1, 3. If I substitute k equal to 2, 5. All right. So, show that the square of the odd integer is of the form 4q plus 1. Square of this is x, odd integer, squaring it, a plus b whole square, 4k square plus 4k plus 1. In this, I'm taking 4k as common in this. So, it becomes 4k plus into k plus 1. All right. So, this k into k plus 1 can be considered as q. All right. So 4q plus this 1 is available. That's how we got it. 4q plus 1. What is the requirement? We just have to segregate the terms, whatever they give. If they are given cube, we have to proceed with cube. Again, we'll be taking commons and substitute a individual value for those, and you'll be getting the result. Right? Okay. Euclid's division algorithm. In the previous section, we have studied about Euclid's division lemma and its application. We now study the concept Euclid's division algorithm. The word algorithm comes from the name of the 9th century Persian mathematician Al-Khwarizm. An algorithm means a series of methodical step-by-step procedure of calculating successively on the results of earlier steps till the desired answer is obtained. Algorithm. From first step, we will be getting the answer. Is this the desired answer? If not, we will be moving to the first step again. With this data, we'll be moving. We'll be checking if yes or no. If yes, we'll be giving it as an answer, or else it will be a loop. It will be traveling. This is what a programmer does. All right. The same, a step-by-step procedure for calculating successive result. From the earlier step, whatever result we get, we'll be applying that and proceeding. Applying that and proceeding. Right. That's what we'll be doing. Euclid division algorithm provides an easier way to compute highest common factor HCF of two given positive integers. Let us now prove the following theorem. If a and b are positive integers such that a equal to b q plus r, then every common divisor of a and b is a common divisor of b and r, and vice versa. We got a and b, isn't it? Now, after dividing, you'll be getting a quotient and remainder. All right, remainder. Next, what happens? This b would become numerator. Q would become, r would become the denominator. All right, until we successively get the remainder as 0. Until we get 0, we'll be proceeding that step. All right, for what value of this we get 0 would be the highest common factor. All right, first step, a equal to bq plus r, where r is greater than or equal to 0, lesser than b. Here q is the quotient, r is the remainder. If r equal to 0, if you get r equal to 0, then b is the highest common factor. Immediately, the first step itself, you get 0. Then b is the highest common factor. Otherwise, next, what happens? Divide b by r. Then according to Euclid division lemma, it is b equal to r q1 r1. Okay, q1 r1. So again, we'll be checking if r equal to 0. If r equal to 0, then what we divided with, this is the highest common factor. If not, we'll move to the next step again, until finally we will be getting 1, at least 1. The final step would be 1, definitely. All right, that is if there is no other common factor like prime numbers, or prime numbers we can say, or is coprimes. If the highest common factor between two numbers is 1, then they are known as coprimes. See here, 15 and 8, both are composite numbers, but the highest common factor is 1 between them. So these are known as coprimes. We'll be getting this in 6th grade itself, 6th standard itself, we'll be getting all these things. All right, so we'll be proceeding again and again. The above algorithm will always produce remainder 0 at some stage. Hence, the algorithm should terminate. Definitely, it will terminate. All right. The Euclid division algorithm is a repeated application of division lemma until we get 0 remainder. highest common factor HCF of two positive numbers denoted by A comma B. Highest common factor HCF is also called as greatest common divisor GCD. Alright, GCD. Euclid division algorithm is a repeated application of division lemma until we get remainder as 0. The HCF of two equal positive integer k is HCF. Can HCF be 0 between two numbers? It's k itself. See here. Oh yeah, 1. This will be 1. Okay. K dividing k. I'll be getting k by k 1. 0. Remainder 0. Alright. It will be 1. Alright. Highest common factor would be 1. Illustration. Using the above algorithm, let us find HCF of two given positive integers. Let A equal to 273 and B equal to 119. Be two given positive integers such that A is greater than B. First we start 119. 2 times 119 is 238. 238 plus 35. We can segregate it. So we have 35 as remainder. It's not equal to 0. So again, we will divide B. 119 divided by 35. So according to Euclid division lemma, we will be getting 105. 35 plus 35, 70 plus another 35. 105. So the remainder 14. So here too it's not 0. Then again 35 divided by 14. 14 plus 14, 28. So 28 plus 7. Remainder 7 not equal to 0. So again, then 7 divided by 14. 7 into 2 is 14. So we are getting remainder. So 7 is the highest common factor between these two. Okay, that's it. So next one. If the highest common factor of 210 and 55 is expressible in the form of 55 minus x, 55 x minus 325, then find x. Okay, first we have to apply the Euclid division lemma and check. All right, 55 plus 55 is 110. For 4 times we just have to double it, right? It would become 220. So it's not 4. So we would be adding another 55 with 110. So it would be 55 into 3 is 165 plus 45. So now we are dividing 55 by 45. One time only it goes 10. We are dividing 45 by 10. 4 into 10 plus 5. Finally, 5 divided by 10, it gives a remainder 0. So 5 is the highest common factor. What they are told, 55x minus 325 equal to 5, highest common factor. When I take this here, it would become 55x equal to 330. So when I divide it by 55, I'll be getting by 11, it becomes 5 and this is 30. 1 time, 6 times. Okay, that's how you'll be getting the result. All right. Find the greatest number that will divide 445 and 572, leaving the remainder 4 and 5. We are going to divide 445 and 552 with a number. All right. When that number leaves 4 as a remainder for the first one, 5 as a remainder for the second one. So what is that number? we have to get. So if I subtract that minus 4 from this and plus minus if 5 from that, I will be getting the whole value, that is BQ alone. If I find the HCF of these two, I'll be getting the number. Alright, first one 567 equal to 441 into 1 only, 126 would be the remainder. So this is not 0. Again 441 divided by 126 leaves a remainder 63. Again 63 divided by 126 divided by 63, it will be giving 0. So 63 is the, okay, that is the number which will divide, the greatest number that divides this 445 and 572 and leaves a remainder 4 and 5, 63. All right, got it. Here we directly found, the, first we found out the HCF, then finding HCF we applied in an equation to find X. Here we can't have HCF of these two, it will be totally different. They are given a number which divides these two and leaves remainder. So I will be subtracting the remainder to get the overall BQ value. All right. If I get the HCF of this two, I'll be getting the answer. All right. That is what we'll be doing. Okay. This activity help you to find HCF of two positive numbers. We first observe the following instruction. Construct a rectangle whose length and breadth are the given numbers. Try to fill the rectangle using small squares. Try 1 cross 1 square. Try 2 cross 2 square. Try 3 cross 3 square, and so on. The side of the largest square that can fill the whole rectangle without any gap will be the HCF of the given number. If it's 12 and 20, 12 and 20, I have to try 1 by 1, 1 comma 1 small square, 2 comma 2. Take a graph, okay? 12 and 20, that would be a rectangle. If you fill 1 comma 1, everything will be filling, okay? If you fill 2 comma 2, is it getting filled? All right. All right. If you fill 3 comma 3, can you fill it? If it gets filled, then you would be getting, yeah, this is the right result. Definitely 1 cross 1 will be completing all these squares. Definitely it will do. So HCF can be 1. If you try 2 cross 2, is it getting filled up? Then it's okay. This is also an option. Then we have to try 3 cross 3. Can we fill all with that? We have to check. That is just like drawing. How it would be is like this. 12 cross 20. So it will be a rectangle like this. 4, 5, 6, 7. Rectangle like this for 20. Then 1 cross 1 will be definitely filling. The minimum HCF between any two numbers is 1. So next we'll be trying to fill up with 2. 2 would be like that. Okay, like this, I'll be filling everything. If this fills everything, then this is also HCF. So next I will go for 3 cross 3. Okay, 3 cross 3 would be like this. 3, 3, 3, 3. If everything is getting filled, then it can be considered as HCF. So for this particular sum, for this particular question, we can see that it will be getting closed with 4. 3 cross 3 will not get filled. 4 cross 4 will not get filled. So 2 cross 2, that is 2 into 2, 4. That is the answer for this. Here it will be 8. 8 will be filling both 16 and 24. So this is how we can say, if you want to try this activity, you can try. All right. But it's better to understand the theories, how you would be getting the filling up of these length and breadth with 1 comma 1, 2 comma 2. The side or the largest square that can fill the whole rectangle without any gap will be the HCF of the given number. All right. Then theorem 3. If A and B are two positive integers, A greater than B, then GCD of A comma B equal to GCD of A minus B comma B. A minus B comma B. All right. So this is another activity to determine HCF of two given positive integers. From the given numbers, subtract the smaller from the larger number. From the remaining numbers, subtract smaller from the larger number. Repeat the subtraction process by subtracting smaller from larger. Stop the process when the number becomes equal. The number representing equal number obtained in step 4 will be the HCF of the given number. What we have to do? From the given numbers, subtract the smaller from the larger first. Okay. From the remaining numbers, subtract the smaller from the larger. Again, what you get from remainder? Subtract from smaller. What you would get? Again, repeated subtraction should be done. For which number you would get equal? That's the answer. All right. That is, the subtraction will leave 0. That means they will be equal, isn't it? That is the answer. 19 and 15. 75. Okay. 75. Then again, I'll subtract 75 minus 15. 75 minus 15. All right. At last, what I would get, where it will become 60, then 45, then 30, then 15. It becomes equal. That's the answer. All right. So make it simple as possible. You'll be getting the result easily. All right. So that's where we'll be getting. Okay. 80 minus 25, 65. Sorry, 55. All right, 55. Then 55 minus 25, 30. Then 30 minus 25, 5. 5 minus 5 comma 5. So 5 would be the answer for this. Like that we have to proceed. Okay, that's the activity. So there are various methods to find highest common factor. Now we are going to find the highest common factor of 3 numbers. We can apply Euclid division algorithm twice to find the highest common factor of 3 positive integers using the following procedure. First, find the HCF of AB. Call it as D. All right. D is the HCF of AB. Then do HCF for DC. That is Euclid division lemma algorithm for DC. What answer you get, that would be the HCF of 3 numbers. 396, 504, 636. So 504 and 504 and 396. 1 times 108. So 108 and 396. 3 times 72. 72 and 108. 1 times 36. 36 and 72. 0. Okay. Right. 36. Then for 3, 636 and 36. 636 and 36. 36 into 17 plus 24. So 24 divided by 36. 12. 12. 24 divided by 12 gives remainder 0. So the answer is 12. 12 would be the highest common factor of 3 numbers. 2 positive integers are said to be relatively prime or co-prime if their highest common factor is 1, like we told, 8 and 15. All right, 225 and 256. All these are, it would be having lot of things. 3 into 3 into 5 into 5. This is 2 into 2 into 2 into 2 into 2 into 2 into, right? 8 times it comes. 8 times 256. So this has many factors, this has many factors, but both doesn't have any common. Highest common factor is 1. So it is also known as co-primes or relatively prime. Find all the positive integers when divided by 3 leaves remainder 2. Hmm. 6 doesn't leave a remainder 2. See, they are told that the remainder is 2. Okay, we can have, according to Euclid division lemma, it will be like I am dividing it by 3. So the number A equal to B is 3, K plus 2, because the remainder is 2. If I substitute K equal to 0, I'll be getting 0, I will be getting 2. K equal to 0. K equal to 0, I'll be getting 2. That will leave the lowermost number, which leaves the remainder 2 on dividing by 3 is 2. All right. Then if I put 1 here, 3 into 1, 3 plus 2, 5. If I put 2, 6 plus 2, 8. All right. So from this point, we can easily say there is a pattern, plus 3 from the number. So 11, 14, 17. All these leaves remainder 2. If I am asking leaves the remainder 1, then here it will be 1. So 1, 4, 7, 10, All these leaves remainder 1. The same thing can be asked in different manner also. Prove that the product of two consecutive positive integers is divisible by 2. Is divisible by 2. Two consecutive positive integers is divisible by 2. How we can prove that?
Two consecutive positive integers, so 2, 3.
Okay, like 2, 3. All right. See, Amma, if the first integer is 2k for odd number or even number plus 1, this is odd number, and the other number is 2k, even number. All right. If I put k equal to 1, 2, 3 would be the choice. So this will leave 6. Okay. So two consecutive numbers they are specified. So when I multiply this, I'll be getting 4k square plus 2k. All right. So I can again take 2 as common here, 2k as common, and 2k as common, I'll be getting the same 2k plus 1. So this would be leaving a remainder 0 completely. It would be completely neutralized. So it is BQ divided by 2, isn't it? Divisible by 2. So I had to divide by 2. 2 into, if I take 2 as common, it becomes 2k square plus k. So this one is q. It is 2q. There is no remainder. No remainder. That's how we'll be getting this. Okay. When the positive integer a, b, and c are divided by 13, the respective remainders are 9, 7, and 10. Show that a plus b plus c is divisible by 13. What we can do here?
First, we need to find A, B, and C.
Okay.
After that, we should add it and we should divide it by 3 and we have to shift it.
Okay. Right. Leaves remainder 9, 7, and 10. So a would be 9q. Okay, 9q plus 9. Sorry, 13q plus 9. B will be 13. Sorry, 13q plus 7. C would be
13q plus 10.
okay. When I add all this, I can easily say for AQ, there is 13A, 13B. I can take that as common. That number will be definitely divisible by 13. So the reminders 9, 7, and 10. When you add all the reminders,
26.
is 26 divisible by 13?
Yes.
Yeah, that's it. The remainder is all right. So definitely a plus b plus c will be divisible by 13. All right. Okay. That is a equal to 13 q1. It can be any quotient. They didn't say it is a consecutive or anything like that. Plus 9. B is 13 q2 plus 7. C is 13 q3 plus 10. So all these we know definitely when we can take it as common, and it is definitely divisible by 13. So 9 plus 7 plus 10 is 26. It is also divisible by 13. So there is no remainder. Okay. Here, next one would be square of any integer. Any integer leaves a remainder either 0 or 1. A positive integer or negative integer. Sorry, a positive integer or negative integer. It can be odd or even. For odd, we know it is 2k plus 1. For even, 2k. When you square it, when you square it,
And so 4k square minus
okay, then definitely you'd be getting the result. All right. Then we are dividing by 4, isn't it? That value, when divided by 4, leaves only two remainders, 0 and 1 alone. There will not be any 2 or 3 reminders. When you divide a number by 4, we'll be getting the remainder of 0, 1, 2, and 3. We won't be getting the remainder 2, 3 at all. All right. Only 0 or 1 would be the remainder. How we will do it? For odd even numbers, 2k whole square. So 4k square. Here there is no remainder at all. If it's 2k plus 1 whole square, 4k square plus 4k, 4k plus 1, 2ab. In this, I will take 4k as common. 4k as common. It becomes k plus 1 plus 1. This I will substitute as q, 4q plus 1. So it leaves the remainder 1 here. In the previous 2k whole square, it leaves the remainder 0. All right, that's how we have to prove. From here, these are somewhat theoretical. You have to apply your knowledge here regarding squares, how you are going to take. After that only we can proceed. Apply the knowledge there and you would be getting the result. Right? Use Euclid division algorithm to find the highest common factor HCF of these. So bigger number divided by this. Okay, 1 into 340 plus the remainder. All right. Definitely it will leave a remainder. Then 340 divided by remainder. Slowly, one by one, you'll be getting the result. Okay. Find the largest number which divides 1230 and 1926, leaving remainder 12 in each case. Remainder is 12. So I have to subtract 12 from this and 12 from this. In each case, 12 from this, I will be getting two numbers. I have to do HCF of that number. If D is the highest common factor of 32 and 60, then find X and Y satisfying D equal to 32X plus 60Y. How we can find? D is the highest common factor, number 1. All right, number 1. Next, satisfying X plus Y. Find X plus Y satisfying D equal to 32 plus 60Y. Okay. What would be the HCF?
60 divided by 32. Using that algorithm.
Yeah, 1 time 28 would be the remainder. 32 divided by 28, 1 time 4 will be the remainder. 28 will be divided by 4. So 4 is the highest common factor. So D equal to 4. All right. Here we have to assume one value of X and get the value of Y. If X equal to 1, then 4 equal to 32 into 1 plus 60y. So 32 goes here. It becomes minus 28. Okay, minus 28 equal to 60y. The 60 goes here. Y equal to minus 28 divided by 60 minus 7 by 15. It would be divisible by 4, divisible by 4. This would be y. If I substitute x equal to other value, I'll be getting, accordingly, I'll be getting the value for y. All right. Okay. All right.
So then what number should be substituted?
They just ask for x and y, satisfying this equation.
So we can find any number.
Yeah. If they are given that another term also, another equation, they are given another equation also, we can solve simultaneously and get the result. But they are given only one equation satisfying. So whatever value of x you take, accordingly you would be getting the value of y. Let me consider 2 as the option for x. X equal to 2. Then this would become 64. 4 minus 64 equal to 60y. Minus 60, 60y. So y equal to minus 1. If x equal to 2, y equal to minus 1. Okay. All right. Got the result. When you are strong with your result, you will be getting the answers easily. All right. Think about it and proceed in the right direction. Okay. Ninth one would be a positive integer when divided by 88 leaves the remainder 61. What will be the remainder when the same number is divided by 11? Until for 88, 88 is 8 into 11, isn't it? So I divide the 61 by 11. 55 plus 6. 6 will be the remainder. Prove that two consecutive positive integers are always co-prime. Yeah. Consecutive positive integers. We can take
2, 3 will also be.
yeah 2, 3 or 110, 111, whatever consecutive positive integer. You can take an example and prove that also. Let the two positive integers be 12, 13. Okay, like that. 12, 13. So 13 divided by 12 leaves 12 into 1 plus 1. So 1 divided by 12. 12 into 1 plus 0. So 1 is the highest common factor. All right. What we will do, 13 equal to 12 into 1 plus 1. So 12 divided by 1 leaves remainder 0 only. Automatically 1 is the common factor. Like this, whatever number you take, 110, 111. 111 equal to 110 into 1 plus 1. So 110 equal to 110 into 1 plus 0. So 1 is the HCF. Okay. Okay. Factorize the number 240. Fundamentals of arithmetic. 240 can be divided as 24 into 10. Factorizing. 8 into 30 is also possible. 12 into 20 is also possible. 15 into 16 is also possible. Is there any other way? 2 into 120 is also possible. 1 into 120 is also 1 into 240 is also possible. 3 into 80 is also possible. 4 into 60 is also possible. 5 into 40 8 is also possible. 6 into 6 into 40 is also possible. 7 doesn't go. 1 minute. We didn't stop. We stopped recording and paused it, and it's okay. You listen to this, isn't it? That's enough. Then, if the given factorization, find the number m and n. All right, m and n. 5 into 2. This will be 10. All right, 5 into 2, 10. N is 5 into 10 is n. So 50 is n. 3 into 50, 150 is here. So 2 into 150, 300 is the answer. All right, got it? From this itself, we went through. That's what they have done here. All right, next. Can the number 6 power n, n being a natural number, end with digit 5? Can it end with digit 5? 6 power n? No. Why?
The 6 to the power of 2 is 36.
Okay.
So it's not ending with 30. So automatically 36 into 6 also will end with 6 only.
Okay.
So it will not.
All 6 power n's will be ending with 6 only. It's not possible to have 5. First of all, 5 is an odd number. Power of any even number will not be an odd number until that n equal to 0. All right, that itself is the answer. So 2 is a factor of 6 power n. 2 power n, 6 power n. But any number whose last digit is 5 is always odd. Hence, 6 power n cannot be a end with digit 5. 7 into 5 into 3 into 2 plus 3, a composite number. Justify your answer. I can take 3 as common here. 3 as common. So it would become 7 into 5 into 2. 35 into 2 is 70. 70 plus 1. 3 into 70 plus 1. Yeah, definitely. This is getting divided by 3 and 71. Hence, it's a composite number only. If I couldn't get any number, any factors, then it will be a prime number. A and B are two positive integers such that a power b and b power a are 800. Find a and b. Okay, find a and b. The number 800 can be factorized as 1, 2, 3, 4, 5. Then 5 into 5. So we can easily say 2 power 5 and 5 power 2. Automatically from this, a power b, b power a. So a is 2, b is 5. Okay, automatically you will be getting the result. Or b is 2, a is 5. Both will be giving the same result. All right. Can you find the 4-digit PIN number PQRS of an ATM card such that P squared Q R power 4 SQ? Okay.
So we have to factorize.
This is power 3 10. All right. This is power 3 10 can be written as 2 into 2 into 2 into 5 into 5 into 5. So 2 into 2 into 2, 5 into 5 into 5. I'm just simplifying it. So I can easily say this is 10, this is 10, this is 10. So now I have only 315. That is this into 315. If I factorize this 315, what I would be getting?
So we have to factorize.
Yeah, factorize this. Will this 315 get divided by 2?
No, it will go by 3.
Will it divide by 3? Okay. So 315 divided by 3, it gives 3, sorry, 1, 0, 5. Will it again divide by 3? 3, 5. Will it get divided by 3? 5, 7. 7, 1. So 2 power 3, 2 power 3, 3 power 2, 3 power 2, 5 power 1, 2, 3, 4, 5 power 4, 7 power 1. So which is to power 3? 2. So SS 2 in the 4, SS 2. Which is to the power 1? 7. SS, okay. Power 1 is 7. Q is 7. PQ, this is 7. Which is to the power 4? 5. 5. R power 4. 5. 3752 would be the answer. Here I distributed the 2's easily so that the value would be easy. I apply the simple formula 315 into 1000. 1000 is 10 into 10 into 10. Then I segregated that and easily. After that, the sum became easy for us. Or else the prime factorization will be lengthy. 2, 2, 2, then 3, 3, 3, then 5, 5, 5, 5, 5, then 7. It will be a lengthy process. We can easily segregate things like this and get the result. Okay. For what value of natural number n, 4 power n can end with the digit 6?
N is equals to 2.
Hmm. What will happen if n equal to 3? 4 into 4 into 4.
The last number will be 4.
Okay. 6. First one is 4. Odd number. 4, 6, 4, 6, 4, 6. 4 power 1, 4 power 2, 4 power 3, 4 power 4, 4 power 5, 4 power 6. It goes on like this. So, for what value of natural number n, 4 power n can end in 6 when n is an even number. Then it will end at 6. If m and n are natural numbers, for what value of m does 2 power n into 5 power m ends in 5?
The number will 2
Hmm. N is 2.
mm.
M is 2. Okay. Okay. 25. All powers will end in 5. All powers will end in 5. All 5 powers will definitely end in 5. That is not the question. There is 2 power n also.
Then n should be 1.
N should be 1. If n is 1, n equal to 1, then 2 power 1. MS, value of MS 2, 25. So 2 into 25 is 50. Zero.
Power
2 power 0. They are given natural number, not whole number. It should be minimum 1, 2, 3, and 4. Consider n equal to other options. If n equal to 2, 2 power n equal to 2, then m equal to 1. We got 4 into 5, 20 again. Okay, what about n equal to 3? Eight.
40.
Hmm.
So we lost it.
We won't be getting in any place, we won't be getting 5. Is that so? Are you sure about it? Hmm? Yeah, that's the truth. Because anything power 2 into 5 powers will be giving 0 as the final digit. Whatever it is, whatever it is, it will not, if 2 power 1 into 5 power 5 also, 5 power 3. What is 5 power 3? 125. If there is 2 power 1 also, or 2 power 2, 2 power 3, whatever it is, it will get multiplied and we'll be getting 250 only. 0 would be the last answer. So there is no possibility of 2 power n and 5 power m to end with 5, provided it's a natural number. Like you told, if n is a whole number, if I put 0 and m equal to 1, any number of m is a possibility to get 5, or else there is no possibility. Okay. Find the HCF of work it out. Find the HCF of which method you are going to work. Okay. Factorization method also would be fine. Hmm? 10,000. Good. In between itself you found out. Very good. Okay. That's the right answer. But we can proceed from here also. The prime factorization never stops here. This is divisible by 3 and again another 3. Like that we have to proceed. Definitely you would be getting 10,101. No doubt in it. But we should proceed. We would be getting 3s, then 5s, then 7s, 13s and 37. All right. So well done. If 13824 equal to 2 power a and 3 power b, then find ab. Do prime factorization again and again and again. 2's, how many 2's you have, how many 3's you have, you'd be getting this. Prime 1 x1, prime 2 power x2 plus prime 3 power x3, prime 4 power x4 is this one, where p1, p2, p3, p4 all primes in ascending order, and x1, x2, x3 are integers. Find the value of p1, p2, p3 and p4 and x1, x2 and x3 and x4. What we have to do then?
We have to again factor.
Try factorizing. 113,400. அக்கா வெளில போயிருக்காங்கக்கா கடை. All right. Well done, ma. That's what you have to do. You have to definitely cut short it, and automatically now you got the simple questions. From there you have to proceed. Well done. 5. Okay. 6. Okay. 7. Again 5, 6, 7. It will be divided by 3. Okay. Then 1, 8, 9. 189. All right. Again it will be divided by 3. 6, 3. Again it will be divided by 3. 3. That's it. 7, 1. So 2 power 1, 2, 3. 2 power 3. 3 power 1, 2, 3, 4. 3 power 4. 5 power 2. 7 power 1. So P1, P2, P3, P4 is 2, 3, 5, 7. X1, X2, X3, X4 is 3, 4, 2, 1. All right. Like that, you can easily go on with the next fundamental. Find LCM and HCF of 408 and 170 by applying the fundamental theorem of arithmetic. Fundamental theorem, this is prime factorization. First, we have to find the HCF. Then, applying the balance remaining numbers, multiplication of remaining numbers will give the LCM. First, we will do the HCF, then the LCM. What are common for that? We will take all the prime factors which are common. Then after that, we will get the other data. All right. So this is greatest number consisting of 6 digits, which is exactly divisible by 24, 15 and 36. Greatest number consisting of 6 digits What is the greatest 6-digit number?
99,000. Sorry.
9,99,999. All right. That number minus some, which will leave the reminders 24, 15, and 36, or which will get divided by 24, 15, and 36. What is the rule? Hmm?
The same number.
Yeah, divisible by 24, 15, and 36. Greatest number. All right. So try to multiply that number. First, try to multiply the number. All right. So 24 into 15. How we can do? 24 is 12 into 2. 15 into 2 is 30. 12 into 30 will be easy. All right. 12 into 30 will be easy. Then again, multiply the answer with 36. Multiply the answer with 36. Automatically, that would be the smallest number. If you multiply with those that number with any factor, any numbers, it should not exceed 6 digits. That will give the answer.
The greatest.
Yeah, the greatest number. What is the smallest number that divide by 3 numbers, 35, 16, and 91, and leaves the remainder 7 in each case? Now they are told that the remainder is 7 in each case, smallest number. All right. The same fundamental rule. First, find the HCF of this and multiply that and add 7 to it. All right. Multiply that, adds that is LCM. Find the LCM. Multiply all the find the HCF plus 7. You'll be giving the smallest number. All right. Find the least number that is divisible by the first 10 natural numbers. Divisible by first 10 natural number. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Least number which has been divisible. So take LCM of the HCF of this. That will be the least number which is divisible by all this. Will 1 get divided by 5?
Oh.
All right. So 2 into 3 into 5 into 7 would be giving the answer. Because 4, we have 4. So another 2. Find the LCM of this. You will get the least number which is getting divided. All right. So how to find the LCM of this?
You have to multiply.
If you multiply, you would be getting a bigger number. Least number is the LCM. Highest common factor is, okay, least number which that is divisible by the first 10 natural number. If you get the least number, okay, least number is HCF only. Find the HCF of this, you'll be getting the answer. All right. Modular arithmetic. We will see it in the next class. Fine. We will see this in the next class. You try to work this questions. Definitely you'd be having some questions which you won't be having any idea at all. I gave idea for all the questions. You would be completing some questions without any doubts. Some question you would get stuck in between. There'll be a minute point only. So I want to know what and all questions you have doubts in. Which question, ma?
8 plus 8 sum and third subdivision.
Okay. What doubt you have?
How to work it out?
First, I asked you to find f of g. Okay.
After that, but I found I think it's I don't know if it's right.
If it's right, this should be equal. If it's equal, that is right. All right. If it's equal, that is right. There is no option there. If this is not equal, then we have to check where we went wrong, because we know this associative property is always true. All right. You got it right. So no problem. I don't want these kind of scratches. All right. Or like these. Hmm. You may be slow now also, it's not a problem, but it should be crystal clear, just like the sum. All right, just like the sum, you just have to be clear. All right, clear. Definitely you'll be getting the answer. F of g, x squared minus 4. Okay, and f of g of h, 3x minus 5 whole squared minus 4. Yes, 2 into 5, 10, 10 into 3, 30. You can do here itself. Yes, multiplication or a plus b whole square or a minus b whole square, 2 into a into b, isn't it? 2 into 5, 10, 10 into 3, 30. You can put minus first because it's the sign. 2 into minus 5 into 3. So minus first, 10, 10 into 3, 30, then plus 25 minus 4. Okay, got it right only. All right. I think first you got confused here. You have substituted vice versa. All right, vice versa. You have substituted this value in h. You have to substitute h value in f of g. That's it. Apart from that, it's fine. For all kinds of a plus b or a minus b whole square, so here 2 into 4 into 1, 8. You don't have to go deep into it. This is giving one step, isn't it? 2 into 4, 8, 8 into 1. In any other question also, you can get. So 2x plus 8 whole square, 16, 2 into 8, 16, 16 into 2, 32. That itself you'll get. So you'll be, one step will be reduced. All right, one step would be reduced. So when you do that, you will be getting strong answers. Here too, when you get stronger, you can directly write 2 squared x squared, 2 squared 4 x squared. Go one by one. 2 squared x squared, 2 whole squared x squared. So 2 squared is 4, x squared is 4. Right, like that. When you work like that, one step will be minimized and your time consumption would become easy. All right, this is how you can segregate your score. Yeah, you completed that one too. Very good. Mm. Did you analyze yourself? 10 minutes you completed this. And where and all you went wrong and then corrected yourself. Here, all right, here, here, this one, all this should be considered error only. All right, because if we are that strong, you won't be doing these mistakes at all. All right, we have to calculate how many errors and everything by ourselves. So 90, you have taken around 11 minutes, not 11, 16 minutes to complete. So 90 questions, you're taken 16 minutes to complete. So how much time you're taken for one? So you can add that as compensation. All right, you are the one who is going to judge. I don't want other people to judge you. You judge it yourself. All right, actually time taken is 16 minutes. 16 into 6. What is 16 into 6? 96. Okay, 96. That is for this exercise. 16. Okay, sorry. 16 into 6, 60. This will give the total in seconds. Total 90. So 0, 0 get cancelled 3 times. 3 3s are 3 2s are. So 32 divided by 3. 32 divided by 3. 32 divided by 3 is 10, 2 by 3. Okay. Now we did this modulo at this Euclid division lemma is in 10, 2 by 3. That is 3 into 10 plus 2. Okay. 10, 2 by 3. That is 10.66 seconds you have taken for each one. Right. That's the time which you have taken for completing this. So these should be considered by as errors. I'm just notifying you, and this one also will be considered as error. I can't specify whether this is 3 or 8 or 0. All right, 3 or 8 or 0. Why this should be considered as error is we ourselves will be, while we are working in next step, we ourselves will consider that as 0 and proceed with the sum. So that's why the number should be pretty clear while you are working. All right, and there should not be any strikeout. If there is any strikeouts like this, it should be a complete strikeout, not one digit strikeouts. All right, complete strikeouts, and write it clearly, fresh. And you should not scratch it 1, 2, 3, 4. Only one should be there from here or here. Only one should be here. Lot of things should not be done, and the space should be below, quite below that. Leave another line and start with the next one. All right, that will give you a better idea. Nice. In 44 minutes you have completed. 42. 19 plus 9 plus 13. In 42 minutes you have completed this. Very good. So now you would be having an idea what kind of questions you can expect in future and how to factorize those questions. So you'll be answering it immediately. Okay. Mostly you would be getting 3, 4, 2, 6, and so on. You have done a bigger number of factors also. So whenever you see a question, you can easily say, oh, it can be divided like this. So this is the answer. All right. Very good. And your negative errors are minimizing. You're not scratching and writing your negatives. That's well and good. That's a very good improvement. Well done. All right. Okay.
I'll take it or
That's for you. That's for you. You file it, you will understand where you're going wrong or where you're going right. Right. Thank you. The next part would be easy when you understand. All right. That part is arithmetic progression, sequence and series, then arithmetic progression, geometric progression, sum of AP, sum of GP, then special series. That would be kind of fast because it's full of numbers only. So you can easily work out it. Okay. Done. All right. Okay. Thank you then. Bye bye.